name is Mark Barnes. I get the pleasure and privilege to kick off the first half, so I appreciate everybody's time today. I'm about 3 hours behind most of the folks on the call here. I'm based in Vancouver, BC, where it's nice and sunny this afternoon. So thanks for joining us. Yeah, so what I want to talk about is I want to talk about bearing lubrication. Specifically, how do we set up bearings for good lubrication practices? What do we need to do for success? And we have a short session today, so I'm going to focus specifically on rolling element bearings, and as a subset of that, predominantly rolling element bearings that are using grease lubrication. But to kind of set the scene here, this is a study that was published back in 1996. It was conducted by SKF. And it's probably the most comprehensive review of bearing failure data from the field. And as you can see from the pie chart, there are many different reasons why bearings fail, from installation issues, alignment issues, even issues related to how we store and handle the bearing before we even put it into service. But germane to this conversation, I want to focus on the blue area, and in particular the dark blue segment. So if you look at that blue segment there, you will see that in this particular application, again, these are large rolling element bearings used on paper machines. It's estimated that around 34 or 35% of rolling element bearing failures in that category are due to inadequate lubrication. Now that's a large catch-all. It includes everything from incorrect lubricant selection to over lubrication, under lubrication, lubrication starvation, and several other issues. The second one on that, by the way, is contamination, which is also a very important mode. But today we're going to focus, or this afternoon, we're going to focus on how do we get those 35% of failures that are due to inadequate lubrication. How do we bring that number down? How do we properly engineer and design lubrication for rolling element bearings? So I want to start off going back to first principles. So when we think about a rolling element bearing, we're thinking about the rolling contacts between the element itself, whether it's a ball bearing in a deep groove ball bearing, or a cylindrical rolling element bearing, or any other rolling type bearing where we have two raceways and separated by the rolling element. So when we talk about lubrication, obviously what we're trying to achieve here is separation between the moving components. So that means, in this instance, between the rolling elements and the raceway of the bearing, as well, of course, other contact points within the bearing, like the cages, as another example. So this is definitely something that we find within the load zone of a rolling element bearing. But just for general interest, this is also found anywhere where rolling contact would be found. So certain cams would show the same effect, as would the pitch line of gearing. So anywhere where two mating surfaces are approaching each other in a perpendicular fashion, the ability to prevent wear at that point is due to this phenomenon called elasto-hydrodynamic lubrication. And it works by the oil itself changing viscosity with applied pressure. So if you look at a typical rolling element bearing, the pressure at the contact zones, depending upon the design of the bearing, the load, and so on, could range anywhere from 50,000 to 500,000 psi of pressure. Under those pressures, the oil transitions instantaneously from a liquid to a solid, and then back into a liquid when it exits the load zone. So this is how this lubricant actually functions. It changes its phase during that pressurization event, and actually elastically deforms the rolling elements of the raceway to disperse the pressure over a wider area, thus preventing fatigue-related failure within a bearing. So in general terms, that's what we're trying to achieve here. We're trying to separate moving surfaces through an elastic deformation, and that elastic deformation is caused by the presence of a lubricant. What I should say is that occurs whether it's a liquid lubricant, an oil, or a grease. A grease is nothing more than a liquid lubricant and oil dispersed in a thickening agent. So both grease and oil lubricated bearings function in exactly the same way. The most fundamental property of getting good lubrication is to ensure that we have the correct viscosity for the applied load and speed. And those three factors, so rotational speed, viscosity of the lubricant and operating temperature, and the applied load, Those three go into helping us select the correct viscosity for the application. So when we think about that, we can refer to a graphical representation of bearing lubrication that's referred to as the Strivet Curve, named after the researcher that developed this theory. So if we look at the Strivet curve, we can look at two axes. So on the x-axis is this concept of speed multiplied by viscosity divided by load. And then on the y-axis is friction within the bearing or within the machine. So a couple of things I want to point out. First of all, let's assume that our bearing is at rest. The machine is shut down, so the speed is obviously 0. When we first start up a machine and the bearing is turning fairly slowly, there is not enough speed to create complete separation between the moving surfaces. When we don't have complete separation between the moving surfaces, we're going to find that one asperity on one surface is going to come in contact with an asperity on the second surface and create what we refer to as mechanical friction. And this is found under conditions where we have very low speeds, we have perhaps too low viscosity, too high a load for the application, or we have a lack of lubrication. But anywhere where two surfaces come in contact with each other, we refer to that as boundary lubrication. It creates mechanical friction, and that mechanical friction generates heat, and of course will induce wear within the bearing. If we select the lubricant correctly, meaning we select the right viscosity for the machine's design speed and design load, what we find is that as speed increases, the friction, the mechanical friction, will start to drop, and that's the drop from the initial high point to a low point here, the valley, if you will. And that reduction in friction is due to the fact that the viscosity is creating this separation between the moving surfaces, and we're slowly creating more of a gap between the surface that is rotating relative to the surface that is stationary or moving at a slower speed. So that's kind of how the friction changes from pure mechanical down to kind of the low point in friction. But actually, if you increase speed from that point, what you actually find is that friction increases again, which may seem kind of counterintuitive, because you would think that once the two surfaces have been adequately separated by a lubricant, then there shouldn't be any friction. But in fact, there is friction, and that friction comes in the form of fluid friction. You see, when oil rotates inside a bearing, there are distinct layers and molecules of oil that are moving relative to each other. And of course, whenever we move two things relative to each other and we create movement, then we create rubbing, and that rubbing creates friction. In this case, the rubbing is between two layers of oil, which we refer to as fluid friction. So in this dynamic, obviously our goal is to avoid wear within the bearing. So we certainly want to avoid mechanical friction, but we also want to avoid fluid friction. Our goal is to work somewhere in the middle, not quite at the bottom. We want to have a little bit of a margin of error, but we want to sit somewhere in that midpoint range where we have a minimum amount of mechanical friction and we don't have excess fluid friction. So from a theory perspective, that's what we're trying to achieve. So how do we do that? Well, there are certain things that we go through, and in this session, we don't have enough time to go through in great detail all of these, but the first choice is to decide whether the bearing should be lubricated with oil or grease, and there are criteria that we look at for that decision. The second, which is the most important, which is what is the viscosity of the lubricant that we're going to use. The third is what kind of additives do we want. Fourth is how we're going to apply it, and then if it's a grease, we need to think about the thickness or the grade of thickness we're going to use, the type of thickener, and then most importantly, the volume and frequency of that grease. So as I mentioned before, our goal here is to create separation between moving surfaces, but not so much that we have fluid friction. And there's a term for that. We call this kappa. So kappa is the ratio of the optimum viscosity for this application divided by the minimum. And the minimum just means what is the least amount of viscosity that will create separation. Right? So when we say a kappa is 1, what we mean is that the actual separation, the actual viscosity at operating conditions is exactly the same as the minimum. So we just about have separation between moving surfaces. Now, in theory, that may work. In practice, because not all surfaces are completely flat, we want to actually operate at a kappa above 1 so that we have a reasonable margin of error. An analogy I often use when I talk about this is, think about flying. As you heard, I live in Vancouver on the West Coast, so when I'm flying to Ontario and I fly over the Rocky Mountains, if I'm at 12,001 feet above the Rocky Mountains and there's a peak which is at 12,000 feet, in theory that works. In practice, probably not very good safety margin there. So we want to be at a higher altitude. In this case, we want to have a safety margin so that the surfaces have at least 2 and sometimes as much as 4 times the separation that theory would call for. So again, we want to operate in that kappa range of anywhere from 2 to 4. Fortunately, smart folks have figured all of this stuff out, so we don't have to do a lot of detailed engineering calculations. Bearing manufacturers have readily available information that you can use. This is a nomograph that is from SKF. Looks complicated, but it's actually pretty simple. What you need to do is to determine the bearing dimensions, either by measuring it or obviously looking at the bearing number in a catalog. But either way, we need to know the dimensions of the bearing, meaning the outside diameter, the inside diameter, and we actually add those two together and divide by 2. And that gives us what's called the mean pitch diameter, or D subscript M. So once we have that number, we then use the nomograph from SKF and we go along the bottom x-axis here until we find that DM value. So in this case, let's say it's 400. Once we hit that DM value, we go straight up and we look for the sloping blue line that represents the speed of rotation of the shaft. So in this case, if our DM is 400, the shaft is rotating under operating conditions at 500 RPM. Go straight up, we meet the line, and then we go to the left. And you can see there in this example, we read off that the minimum viscosity requirement is 10. So if we are trying to select a kappa value that's 2, in other words, it's twice the minimum, if this nomograph says the minimum is 10, then we need to choose a lubricant that has a operating viscosity of 20. That's what's going to give us a kappa of 2. So we do that by looking at the viscosity temperature profiles of the lubricant, whether it's an oil or base oil viscosity of the grease. And I won't go through the exercise, but we have to look at the different lubricants that are available to us, look at how the viscosity profiles change, and then we look at the operating temperature of the bearing. So if it's operating at 75 degrees Celsius, and we want to have a kappa in this example of 4, we need to be at 4 times the minimum. So remember, our minimum was 10. 4 times the minimum obviously is 40. So we can then go ahead and see which lubricant is closest to us, and that's how we select that right viscosity grade in order to maintain that separation. But the other factor with grease in particular is not just getting the right lubricant selected, the right viscosity selected. It's really more about how we adequately grease that bearing. And more bearings fail, grease lubricated bearings fail because of inadequate greasing than those that fail due to poor lubricant selection. Really, real quickly, what we need to think about is 2 things. First of all, how much grease do we initially pack into a bearing? So if it's a bearing that needs to be greased, the decision about how much we pack the bearing depends upon the physical size and the speed of rotation of the bearing. If the bearing is very small and or turning very slowly, we would literally pack the whole thing with grease and we're good to go. But as the bearing gets larger and or the rotational speed gets higher, we need to think about the internal frictional force that's generated, because that can create heat and other problems that create just as many problems as lack of lubrication. So we can choose how much we initially fill based on, again, the size of the bearing and the speed of rotation. And I put this here, I don't intend to go through the engineering, but I put it here because some of you may request the slides. I'm happy to give you the slides afterwards. So I wanted you to have that information. But again, bearing size and speed is what determines the volume of grease that we initially fill. But then perhaps the most important question is, how much grease do we reapply and how often do we reapply? And that's oftentimes the part that's missed the most. Old school mechanics out there will tell you grease the bearing until grease comes out of the seal, and then once you see it coming out of the seal, add another couple of pumps for good luck, and then you should be good to go. Well, I think most people now would recognize that that is not best practice. Particularly for higher speed, more critical bearings, we want to be a little bit more precise in how we grease a bearing. So again, smart folks have done the engineering for us. So in terms of calculating the regrease volume, there is some very simple calculations that we can run. In order to do this, you simply need to know two things. You need to know the outside diameter of the bearing, as well as the thickness or the width of the bearing. So that's capital D and capital B on my slide there. Once you have those two numbers, and depending on whether you want to work in millimeters, as we tend to do in Canada, or if you're in the US in inches, you apply either the first or the second formula there. So in millimeters, we take the outside diameter of the bearing in millimeters, the width or the thickness of the bearing in millimeters, we multiply them together, and then we multiply by a factor of 0.005, and that gives us the required regrease volume in grams of grease. Once we have the grams of grease, we can convert it to shots of grease, and that's how much you apply every relubrication interval. Question is, how often is that relubrication interval? Well, that depends upon the service life of the grease. Generally speaking, the higher the speed, the larger the bearing diameter, meaning the more contact area, and the higher the degree of vibration or heat or contamination, these all impact the life of the grease. So if we have a shorter grease life, we want to regrease more frequently in order to take care of this, right? So in the case of higher speed, the higher the speed, the more often we grease. The larger the bearing, the more often we grease. So we calculate this based on these different parameters. Again, there's some simple math, some simple engineering that we can apply to this. This was developed many years ago by a lubrication engineer by the name of Tex Lugner, based out of Calgary, Alberta. And he came up with a simple formula that you can see on the right-hand side here, which essentially uses three inputs. It uses the rotational speed in RPM, it uses the shaft diameter in millimeters, and then uses a bearing factor, which depends upon the type of bearing. So whether we're using a ball bearing, a cylindrical roller bearing, spherical or tapered roller bearings. So again, I won't go through the math, but we can just plug the numbers in there. And what that will kick out for us is a estimated regreasing interval in hours. Okay, so that gives us an idea to say, hey, we know how much because we've calculated the volume based on the physical dimensions of the bearing. We know how often, we've plugged the numbers in, and now we get a reading that says, hey, you got to add 10.3 grams of grease every 3 months. So that gives us a really good baseline to go ahead and develop our lubrication PMs around that scheduled interval. One of the things when we apply these formulas that we often take account of are different conditions. These calculations are not exact engineering. They are plus or minus, I was going to say 10%, but in reality, plus or minus 20%. Sometimes they're a little under, sometimes they're a little over, but they're kind of order of magnitude where we want to be. So if we look in the real world, real bearings, they operate at different temperatures. So if a bearing is running at a hotter temperature, we may reduce the regreasing interval as calculated by the formula. If the bearing is in a high moisture environment, it's very humid, or it's in a washdown environment, we want to regrease more frequently. The bearing is in a heavily contaminated area, we may grease more frequently. If the bearing is oriented in a different way, right? So if a bearing is mounted on a vertical shaft, every time we apply grease to a bearing on a vertical shaft, gravity is not our friend. It's going to allow the grease to fall out of that bearing. So for a vertically mounted shaft, we will regrease that bearing more frequently. A good example would be a water intake pump. If the machine is vibrating, I don't mean that there is a vibration analysis problem, but if it's something like a vibratory screen or something that has natural vibration, that's going to create shearing force within the grease. So we grease more frequently. If it's poor quality grease, or if the bearing is turning very slowly, oftentimes these calculations don't work very nicely. Okay, so all of these engineering calculations that have been provided by people like SKF and FAG and NTN, all the really smart bearing guys, all they're really doing is trying to come up with a best case estimate based on theory of how often and how much you want to apply grease. But I want to take you back to maybe the first or second slide. Think about what we're actually trying to do by applying a known quantity of grease on a known interval. What we're trying to do is ensure that we certainly don't work in the low range, the low end of the Strivet curve, because if we have metal to metal contact, we're going to get friction, we're going to get wear, and we're going to get a reduced bearing life. So we certainly don't want to work here. As we slowly apply grease, obviously we're going to create separation of the surfaces, so mechanical friction will come down. If we over apply grease, so we pump grease until it comes out of the seal, then we start going off into the opposite direction. We start creating churning internal mechanical friction. So all of these calculations are trying to do really is trying to ensure that we operate in this sweet spot, this low friction zone within the Strivet curve, right? So that's great in theory. Wouldn't it be great if we could actually measure this in the real world, in actual application? Of course, the good news is we can do that. And the way we do that is through ultrasound. So I'm going to turn things over to Blair, and he's going to talk a little bit about how we can add precision to greasing of bearings through the use of ultrasound technologies. So I appreciate if you have any questions for me, I'm happy to take them at the end. But Maureen, let's turn things over to Blair.
Well, thank you, Mark. That was an excellent segue. That wasn't planned, so that was fantastic, and I took some notes there, Mark. So thank you for that. So my name is Blair Fraser. I'm the director of global IoT solutions at UE Systems, and I've been in the maintenance and reliability community for a number of years. But I am by no means what Mark was referring to as those bearing experts, right? I'm on the technology side, and nor am I an expert on specifically around, those calculations that Mark was talking about. In fact, it brought me back to my younger years in school, starting to glaze over a little bit there, going, oh, geez, hope there's not a quiz at the end of this webinar. So as Mark alluded to, we're going to talk about ultrasound and how we can use that to further optimize our lubrication program. And really, when we look at it is, when you look at why bearings start to fail, as Mark was talking about, is we know this. It's different studies come back with different numbers, but the large majority is around lubrication. And what I'm seeing in the market today, and it's not a bad thing from technology, is that we're really focused on picking up when a defect happens, but really what we should be trying to focus on, or at least putting more attention on, is trying to eliminate that failure from happening in the first place. And that's what really lubrication is trying to do. Now, when we talk about ultrasound and what we're doing with ultrasound, this goes back to studies way back in the late 60s, early 70s, kind of the same time for your RCM people out there that, Nolan and Heaps came out with RCM. And the study can be traced back to NASA. I wouldn't recommend reading that study because the intent wasn't around ultrasound and early bearing detection. It's a very boring read, if I can put it that way. But what the studies come back is showing you, and now there's many different PDF curves in terms of a bearing failure, and ultrasound is always showing up as that first sign that there's an incipient or initial stage of bearing failure, right, before we start to have a change in vibration and temperature. And really the fundamentals around it is we're looking at a very high band of frequency. So we're looking at 22 kilohertz and above. In this case, in bearings, we're up in the 30 kilohertz range. So obviously our ears can't hear it, right? We're not going to walk by. If you walk by a bearing, and most of us have done that. In fact, as I was prepping for this, we have a demo system in our New York office where we can flush out the grease of a bearing using some degreaser that smells really nasty. And as the person was doing this, I could actually hear the bearing. You didn't need ultrasound to do it. I could tell that there was metal on metal. But in this case, what we're doing is we're looking at a sound obviously we can't hear. And what we're doing with that measurements in terms of that sound or the level of that sound is measuring the friction, right? And that's exactly what Mark was talking about. So, we've been pushing condition-based maintenance, right? If you want to use that term, or predictive maintenance. And what we do with that is we try to look for a meaningful indicator that we can measure, right? And ultrasound allows us to do that with friction. So what can friction tell us about a bearing? So poor lubrication or unideal lubrication, including under or over lubricating, as Mark was talking about, because we see this, and I'll have some examples of that, is you can restore that friction to an optimal level, but if you keep pumping away, you'll literally watch that friction start going up every time you squeeze that grease gun or that single point lubricator is putting grease into that bearing. Right? So that friction is very indicative of not just the health of the bearing. So obviously, if you start to have impacting and friction in the bearing, that bearing is starting to go down that failure curve, but also to be able to tell you two very important things. So using friction as an indicator, you know precisely when lubrication is required. So you're essentially taking the guesswork out of the re-lubrication intervals, right? Because you're monitoring the friction and you will see that friction change, and I'll show you a lot of use cases of showing you that friction change over time. But because we're monitoring that friction, we can watch that friction go down into what Mark called that sweet spot and make sure it stays there. So when we look at this, now this was a study by SKF in terms of, you know, really what's causing that 80% of issues leading to premature bearing failure, right? And the insufficient or too much lubrication is a small part of it. We also have to think about unsuitable lubrication that Mark was talking about, getting the viscosity right and the selection of grease, and contamination is also a big one as well. So when we look at this objectively, right, and we had to do this as a company because the grease caddy is a product we sell, and we have been positioning this as best in class, and you know, it is a good option if you have a lot of bearings and you want to start using friction as an indicator of when and how much grease to provide. So if we look at traditional time-based, right, because there's so much subjectivity to it, you know, and you're walking out there with the grease gun, and the way a customer's described it to me once is, have you ever seen a lube tech or a maintenance person actually wipe down a Zerk fitting before using it, right? So of course, anytime you go out there, you have a human doing it, there's a potential for error. And then the other side, we've seen a lot of uptake of these single point lubricators or these lubrication distribution systems, which are great, but primarily or majority until the OnTrack Smart Lube, they were time-based. Even if they had a vibration sensor built in, it would start taking the guesswork out of run hours or duty and make sure it's running before you put grease in. But it was still time-based. Now, what these single point lubricators are really good at is if you load them properly and install them properly, they're going to make sure every time that grease is put in, it's using the right grease, and you know, potential for contamination is eliminated, assuming proper installation. Then we get over to the grease caddy, right, where we're actually strapping an ultrasound sensor to our grease gun. We're listening to that bearing as grease is entering that bearing, but of course, you still have the issues you can have with the grease gun. So what we try to do, or what we've done with the OnTrack Smart Lube, is merge the benefits of the grease caddy and the single point lubricator together. And with the way ultrasound works, now this is documented in a ISO standard, right? So this isn't something we've pulled up out of the air. This is documented in ISO standard, and everything is based off a baseline. What is our ideal friction? And getting that ideal friction is a little challenging, because often when we start to use ultrasound, we're not on, you know, a perfectly packed, well-installed bearing. The bearing's been out there spinning in a circle for a lot of hours, or in some cases years, right? So you don't know if it's in that sweet spot that Mark was talking about, right? And I'll address that a little further in terms of how to set the baseline. So what we see is when we set that baseline, if we can identify what that sweet spot is, when we see an 8 decibel increase in that friction, that's the first indication to us that it needs lubrication. Now, this does not mean that you have to go out there and lubricate right away, right? It doesn't mean, you know, this bearing, if you don't get out there right away, it's going to fail. It's the first sign that that thin film of lubricant Mark was talking about on those rolling elements is starting to wear, starting to go away. We're seeing a little more friction. And then when we see a 16 decibel increase, that's our indication that we're going beyond a lubrication failure mode. Okay, and what we can see in this case is we're actually causing some secondary damages to that bearing. And what can happen there is you can actually lubricate that bearing and bring that friction back down, but not to the same extent that you were able to drop that friction. That friction will go back up. It's not going to stay down. And then when we see a 35 decibel increase in that friction, this is when you need to start taking some action. And in between that 16 and 35, depending on the failure mode of that bearing, you will typically start to see the bearing running hotter, starting to see it move to pick it up in friction and things like that. So the way I like to describe this is, imagine you're able to use ultrasound, so you're listening with your Superman ears and you're listening to that bearing 24/7. Can you imagine if, so in this case, the baseline was reading 26 and now it's reading 28.7. You're within that 8 decibel range of baseline, right? That's a healthy bearing, do nothing. If that arrow was straight up, right, you're in the needs lubrication. And this is when you would actually go out and apply lubrication. So if you can imagine for me, and you know, just to start to imagine that arrow was straight up on a 90-degree angle, so it'd actually be at 40 decibels, right? So what would happen is if you were to walk out there with a grease gun or use a single point lubricant and say, put a little bit of grease in, with every pump of the grease gun, as grease enters that bearing, you will start to see that friction start to drop and drop and drop. That arrow would slowly move to the left. In fact, it won't move slowly. What we've seen, and I'll show you some case studies here, is it actually falls very, very quickly. And it's being able to leverage IoT for this. You can actually see this in real time, and people are often surprised as, do I stop here? Like normally I would have put in 10 more pumps. I'm like, absolutely, you're going to stop there because it's happy. You've restored to where that sweet spot is. Now, if you're, so say you had the ideal sweet spot and you got that friction down to 26 and you kept lubricating, you kept squeezing grease in, or you kept on telling that single point lubricator to put more grease in, put more grease in, you would actually see that arrow start to skyrocket to the right. It's going to blow past the green, it's going to blow past the blue, and it's going to end up in the yellow somewhere. And that was exactly that chart that Mark was showing, is you can get to a point where you over lubricate it, you get to get that fluid friction that's going to happen in that bearing and start to pick up that friction level as well. So this is an example of an ultrasound sensor on a bearing. And in fact, you can see the remote lubrication line there as well. Right? So it sits external to the bearing itself. What is great about ultrasound is very directional. And if you think about it, right, if you put your ear anywhere on this bearing, if it's at that point in its failure curve, you're going to hear it. So we don't have to be worried about different axes of measurement and movement and things like that. And we've seen some very creative ways of mounting the sensors to get out of the way of guarding and things like that, including on the lubrication line itself. While not ideal, if it is the only spot, that is okay. So when we start to look at this friction, I'll explain to you what this trend is looking like. So there's four lines on this graph. The green line, which is covered by the blue squiggly line, is our baseline. The next line above that is 8 decibels above that, which is our lubrication friction level. The yellow is our warning friction level, and the red is our critical friction level. So the blue squiggly line is, we're looking at this trend over 24-hour period. Okay, and what you're seeing is typical of a bearing. Okay, you're going to have some bumps, some impacting. It's not going to be a absolutely 12 decibels and just stay there forever, right? And in fact, this is a variable speed fan, so it's going to go through varying load changes and speed changes as well, right? And as Mark pointed out, as that speed changes, we'll start to see that fluid friction, and we will see it. So ultrasound is impacted by the varying speed, but as that chart showed you, the impact is not as drastic as that mechanical friction that's being produced. So we will see, in this case, we might see from the lowest speed it can go to the highest speed on a healthy, well-lubricated bearing, a change of decibels of about maybe 2 to 4 decibels. And that's what we're seeing in some of these spikes. This is ideally what we would see from a friction level across all of our bearings. The reality is not all are like that. So here's an example of the friction level. Now, in this case, it wasn't in dire need of lubrication, but it was a way to test out the system. So we're trending the friction, and through a single point luber, able to send a command to apply grease. 15 cc's of grease. We're looking at 2 teaspoons of grease being put into that. And you can see the drastic change that happened in that friction once that grease was added. So we were able to get a baseline reading of about 14, or a reading of an average of about 14, and we're able to drop it about 11 decibels. But also you can see the noise starting to go down, right? As a bearing requires lubrication, you're going to see impacting those spikes, those peaks and valleys that's happening in that bearing. So it's not just the overall friction we're looking at too. By trending this data in real time, we're also being able to look at the impacting that's happening in that bearing. Now, if you can imagine, and we do have some audio samples we can send you, if you were actually to play this back as an audio clip, right, the before is going to be a lot of staticking, a lot of bouncing around, and then once that grease applies, it goes nice and quiet. You're still going to have a little bit of static. It's always going to be there. It's inherent in a bearing. There is always going to be inherent friction, but that's what we're trying to do with ultrasound. So this is a great example of a bearing that required lubrication. Now, in this case, lubrication was done through a single point lubricator through the Smart Lube, and you can see the drastic drop in friction the moment grease hit the bearing. And if I was to zoom into this, and if we have time, I'll absolutely will, what you'll see is, most grease fittings are on top of the bearing, right? And then the grease enters the bearing, and the rolling amounts push it around the rest of the bearing and start to distribute it. So what we can see, because we can capture friction readings in this case every second, is the moment grease hits the bearing, it will actually go up a little bit, right? It's going to say, oh, I got to push this all through, and then it pushes it through. So you can see here in a matter of minutes between that grease hitting the bearing and that change in friction, that friction was able to drop dramatically, right? We were somewhere around 24, 23 decibels, and it brought it right down to what Mark was calling that sweet spot. And the important part too is it stayed there. In this case, our baseline friction was 11. We started here, if I'm looking at my right-hand side of the screen here, the baseline friction was 11 decibels. The starting friction when we started to lubricate was 22. And the system automatically stopped lubricating at 12.6. So it got it close to baseline as possible, right? This is ideally what we'd like to see in lubrication. Now that was using a single point lubricator called our MUE lubricator. This is an example of just going out with a grease gun, but still using that friction value. As you can see here, the moment grease was squeezed into the bearing, right? That change of friction. And this is what I call the aha moment for people, right? Because they're seeing this on their cell phone. You can imagine looking at your cell phone, squeezing grease in and seeing that friction change. All of a sudden, all the theory about friction and viscosity and all that kind of stuff is starting to become visualized. You can see what happens when the correct grease, of course, gets entered into the bearing. Now, this is a great example. This bearing did not require lubrication. Didn't stop them from lubricating, because what they found was a lot of chatter, a lot of impacting in that bearing, right? The amount of grease that was entered in this bearing was so minimal, it would be, it'd be something typical you would just wipe away from the end of a grease gun with a paper towel to get rid of it, right? But what happens here is you can see what happened to that friction change the moment just a little bit of grease. Now, if this was me, I wouldn't have focused on this. I would have let it, and you would have seen the friction eventually go up to that nice lubrication and do it. But they wanted to prove a point that friction or the impacting, you could reduce the overall impacting in that bearing just by adding a little bit of grease. Now, to do this 24/7 is going to require a lot of work, and that's, why we created the Smart Lube. But you can start to see, and I think this is a good visual of the impacting before and after lubrication. So here's another great example of that same decrease. This is very, very repeatable of what happens when you lubricate the bearing. In this case, only 7 cc's. Now I encourage you, because I always forget the conversion, look up, I've always dealt in grams, right, or ounces of grease, right? This is such a small amount of grease. It's always surprising how much grease you actually need to restore that ideal friction in a bearing. Now, this is what a bad bearing looks like, right? As you can see, the friction levels in that warning, we have a few spots here that are above the critical because that bearing is bouncing around, right? So just take a look at this trend versus this trend, right? And when we talk about establishing the baseline, even if I didn't have historical and I just looked at this, this might be for 24 hours. I think it's about 24 hours worth of data on this trend, taking data every minute. You can look at this and just say, there is a lot of noise, a lot of impacting happening in this bearing, right? You don't need to do anything else. You don't need to stand on your left foot, bite your tongue to the right to make some sense of this data. This is generally an unhealthy bearing. Is it going to fail tomorrow? Unlikely not. Will lubrication restore this? It might. And that's where I'd recommend going out there and applying a little bit of grease to see what happens if you can reduce some of this impacting and drop that friction. Now, we always get the question, what about VFDs? What about, or VSDs? Anything that can vary in speed or load. And we have very extreme use cases of monitoring this friction in pulp and paper, for example, where there's conveyors, where there's wood chips, where there's things coming down and literally banging into the bearings, which of course is going to create friction, it's going to create noise. We have ways of looking at averaging that values out, but this happens to be an air handler unit, and you'll notice the extreme oscillations in these readings. That's because this is an unhealthy bearing. And what we notice in an unhealthy bearing, so either under lubricated or there's defects within that bearing, you start to get heavy oscillations like this. And you start to track it. If you were to overlay the RPM or load on this same trend, you would find it matches exactly. And if you remember the same fan I was showing you before through the same speeds, it didn't change by more than 2 or 3 decibels. In this case, we're looking at possibly a 15 decibel change. And it's not uncommon to first put the sensor on and see this roller coaster of a ride. Right? I'm gonna say, apply a little bit of grease for me, right? And then what happens is the roller coasters start to be not as fun anymore, right? They start to even out, and eventually they'll get smooth. So this is another example. As you can see here, the bearing was lubricated. In fact, if we used 12 cc's, and it dropped that friction, but it only dropped it down to the needs lubrication. Right? So what can happen in a bearing? The use cases I've shown you, with the exception of that very noisy one, are all ideal situations that we were able to get that friction down to that ideal mark. But what happens if that bearing has a defect? Whether it's an inner race, outer race, a cage issue, it is going to create friction. And unfortunately, lubrication may be able to mask it or do nothing at all. In this case, what we're able to do is restore that friction the best we could. In this case, the system automatically stopped because what it noticed was that as it applying grease, the friction started to go back up again. As you can see here, every squiggly line here is when it was lubricated remotely. So what it does, it puts it into a 1 second update mode. So we're getting data a lot quicker because we want to see the minute grease impacts that bearing. So it dropped and stopped, and it did this automatically, saying, I'm stopping here because the more grease I'm adding, the friction's actually going up. And if you were to zoom in here, you could see some spikes in this. The user didn't believe it, and this user was me. So I said, you know what, try again. And the exact same thing happened. We put more grease in. Actually, I tried one time and said, I'm gonna put a little grease in. Nope, it went up. There's something going on. In fact, the alert we give people is potentially anomaly detected. I don't know if it's an inner race, outer race, it's a cage defect. I just know there's something going on in that bearing where grease is not going to be able to restore that friction. Again, it doesn't mean you need to replace it. It just means you need to keep an eye on this. So here's another use case I want to show you. And again, we're looking at this trend. This trend, and there's a reason I cut off this image. So if you look at this, this looks like a successful lubrication. Look, the dramatic drop in that friction once 4.5 cc's of grease was entered, right? We started at 21 decibels and it got it down to 12.2, only using 4.5 cc's of grease. Fantastic, let's walk away. This is fantastic, everything's good. If I show you the bigger picture, look what happened. So that was, just say around 10:30. By 1 o'clock in the afternoon, or really by 2 o'clock, my friction went back up, right? And it started going all crazy again, right? This is not uncommon on an unhealthy bearing, right? I often say lubrication can help mask an issue with the bearing, but it's not going to eliminate it. It's not going to keep happy forever, right? Grease can fill up some small divots and things like that in the bearing, but eventually it's going to wear off and we're going to see that friction. This is exactly what happened in this use case. So if I was to go back to this slide and say, hey, everything was good, but the reality is no, we need to monitor this not only before, but also after, right? And that's one of the challenges with route-based ultrasound is if you're going around on every month and you're able to get it back to baseline, what happens 3 hours after you did that initial lubrication? Is it still good? If you're not going to go back for another month, you might miss an opportunity to help preserve the life of that bearing. Again, another use case. This is that same. So this was on 0406, so April 6th. Again, we tried it again on April 20th, so not that long ago, right? More grease was added. You can see it drop down, and guess what? It came back up again, right? And this is not uncommon, as I said, and that's really why we built this Smart Lube manual button, because what you can do is you can mask that bearing or try to aid that bearing and comfort it as it's dying, right? So if you want to go there and give it a couple of shots every couple of weeks just to get to your next shutdown and things like that, you can do that remotely, which I think is a huge benefit. So what I'll do here is I'll open it up for any questions, and hopefully you guys have been using the questions. So Maureen, if you don't mind just getting in there and seeing if we have any questions from anybody that's attending for either myself or Mark.
So, okay, so there are a few questions that have come in, and feel free, we've got a little bit of time to add some more. So someone was asking, and this was a little bit earlier, and so, you know, perhaps you've covered it, but always good to revisit some of these things, but someone was wondering, and it was when Mark was speaking about the formulas for your grease intervals and the quantities and things like that. And they were wondering how you should adjust those greasing intervals if you're going to use an automatic grease dispenser. Now that I would imagine is in relation to an automatic grease dispenser that's not necessarily hooked up to like an on-track system like you were talking about, Blair.
Yeah, so if you're not using the online feedback loop in order to set up an auto luber, you would use the calculations that I showed in my section to specifically figure out how much and how often, and then in fact you use those to set the dip switches on the auto luber to set your frequency and in some cases the quantity of grease as well. The adjustments, I think the question was really also about adjustments. So for example, if you calculate that the bearing needs to be greased every 3 months, then you can do a couple of things, right? So if you want to reduce it because let's say it's a vertically mounted shaft, you could do that. Or a simple thing is if it says, hey, add 30 grams of grease every 3 months, you can actually, kind of interpolate between and say, well, if it's 30 grams every 3 months, I'm going to set the dip switch to shoot the grease in every month. But if you do that, you probably want to cut the volume of grease down by 1/3 as well. But again, I want to come back to kind of the closing theme here. All of that is just theory and conjecture. You can't beat measuring it in real time and really seeing what's happening with that bearing.
Okay, great. And then someone else was asking specifically for the on-track, how does it adjust based, so they said, okay, how does on-track adjust based on the friction and needed lubrication when you do have a variable speed motor? So maybe just cover that again. I know you did touch on that, Blair, but it was a question.
No, absolutely. And hopefully you can see my new screen now that's showing some live data coming in, or is it still sharing my PowerPoint?
It looks, hold on a second. Yeah, no, it looks like you're in the UE Insights. Yep.
Okay, yeah. So this is a great example. This is a real life system. I've scrubbed the company name from it, but it is a teaching hospital, so they're okay with sharing the data. So this is actually on an air handler unit. This is the motor loaded and unloaded sign on a variable speed drive. There is no doubt in my mind that this has increased and decreased in speed throughout the last time here. So when you want to see here, like this is a beautiful trend line. As you can see here, the one below it is not. And again, this is a great indication of this bearing, needing lubrication or starting to fail. And the only way I'm getting to know that is if I start to apply some grease to it. So how we start to differentiate. So what we do with that 8, 16, and 35 decibel limits is, depending on the variation we see in friction, is where we'll send our alerts. So that 8, 16, and 35 is merely, it's a guiding point for us. What we can see is we might set our first lubrication limits to make sure we cover the entire operating speed or loads of that bearing itself, because what we don't want to do is set it, only needs lubrication when it's high, and that asset only operates in low speed for a month, right? And it never crosses that threshold. So we may fine tune those limits a little bit, but this is a great example. And when I look at this, as I said, this is a nice trend line. I can see here, it's relatively smooth. But if I was actually to go in and zoom in, and what I'll do here is I'll put it to auto. It is moving and bouncing around quite a bit through those speed changes. It's just, we were so zoomed out, we couldn't see it. So looking at this, and this is where you can pick up belt slippage and things like that, because if we see, and we actually had a use case where the drive end of a motor was driving a belt that drove the fan, we saw the drive end of the motor and the corresponding end on the other belt on the fan actually impacting at the same time, and we're seeing that belt slippage come through, right? So this is how we can start to use this data from a VFD or VSD point of view.
All right, great. Well, I think that kind of covers it. And obviously, if folks have more questions, I think we'll have a slide maybe at the end where folks can get in touch with the presenters, and of course, linking up on LinkedIn with both Blair and Mark is always a great idea. And then you can, go right to the source. But yeah, there's some contact info there. So there you go. I'll leave it to you guys to wrap it up.
Okay, Sean, over to you for some closing remarks.
Excellent. Blair, Mark, thank you so much. I mean, this is great information that anybody who's tuning in or is going to tune in later on is going to appreciate. At the end of the day, we see how lubrication, how important it is to not only lubricate properly in terms of amount, but also when. The big questions are always asked, when and how much. And I think both of your presentations cleared up that in a lot of cases, and maybe getting rid of a lot of, if not decreasing a lot of failure amounts. So really appreciate it. For those of you who want to contact Blair, his email is Blair, BLAIRF, @uesystems.com. So if you have any direct questions, please direct them to Blair. And Mark, if you're still on here, what's the best way to contact you?
Yeah, they can reach me at my email, which is mark, mark.barnes, BARNES, @descase, that's DESCASE.com. So mark.barnes@descase.com.
Excellent, thanks very much. And if those of you, if you're not seeing the recording or hearing this, definitely look Blair and Mark up on LinkedIn. You'll see some great information on their LinkedIn pages as well. So definitely look them up. As for closing out here, we want the SMRP Ontario chapter want to thank all of you who have attended. For those of you who are new to our chapter, we've been around for quite a while. You can see on the screen here, I'm not going to go through everybody here, but obviously my name is Sean Miller. I'm the vice chair. You can see our treasurer, secretary, and chair who couldn't make it tonight, as well as our general executive. So you can definitely contact us as well if you have any questions about what was presented today, also about anything you want to see presented later on down the road through our SMRP chapter. So feel free, and if those of you who are interested in even being part of our chapter, definitely feel free to contact us. Thank you again for being part of this tonight. We thank Blair, we thank Mark, and also Maureen. You heard Maureen in the background there is from UE Systems as well, and also I believe is part of the SMRP National. Thank you for being part of this, and if there's any questions, please feel free to contact us. And again, just so you know, this has been recorded, and we will make sure the recording is available to everybody who has attended and anybody who hasn't. So thank you very much for all of you, for depending on where you are. Have a great night, evening, afternoon, and morning. Take care.